Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on Auger. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Brad Burrows, specialist at EAG Laboratories.
Thank you, Rena, and hello, everyone. Welcome. I hope everyone is staying safe and healthy out there. I hope you can hear me okay and you can see my screen okay. Welcome to another of a series of webinars dedicated to exploring the Smart Chart, which is a descriptive graphic that shows the capabilities of all the techniques we offer in one figure. Today, we are going to explore one of the most useful of all the techniques, Auger Electron Spectroscopy, also known by the acronym AES, or just plain Auger. And by the way, I often get asked about the pronunciation of the word Auger. Although it is spelled like those large drilling tools, it is named after the French physicist Pierre Auger, who correctly explained the origin of secondary electrons that were spontaneously emitting from ionized atoms in these Wilson cloud chambers. So these electrons were named after him, and I will soon share his explanation for the phenomenon in this webinar. Okay. I graduated from the University of Arizona with a PhD in analytical chemistry, where I used Auger to characterize anode surfaces in primary thermal batteries. I have over 20 years experience in materials characterization using primarily surface analytical techniques. I have specialized in Auger analysis for about 13 years here at the Sunnyvale, California location of EAG Labs. And here's a brief summary of what I'd like to present today. We'll start off with an introduction to our company, and then I'll explain what the Smart Chart is and where Auger fits in this array of techniques we offer. I will then briefly touch on some of the principles of the technique, explaining how it occurs, how we are able to detect the Auger electron, and what the data looks like. I will spend most of our time together presenting examples of Auger analysis results that are typical applications and a couple of outstanding examples where Auger was uniquely suited to capture these results. I then summarize the strengths and limitations of the technique and point out some complementary techniques that can broaden your knowledge of your samples and sometimes overcome the limitations that Auger has. Now, here's a little bit about our company. EAG Labs has multiple locations in the US, Europe, and Asia. We have over 600 highly educated employees using many techniques at 20 plus locations, serving over 4K clients in 50 countries. This company has made a considerable investment over the years in acquiring analytical capabilities with multiple instruments of almost all of them. We can offer parallel analyses of your samples for higher capacity, and we have plenty of backup when an instrument goes down. And this is especially true for Auger instruments, where we have them located here in Sunnyvale, California, down here in Los Angeles. We have multiple systems in Minnesota and in New Jersey, and we also have systems in the Netherlands and in Shanghai. Okay, let's take a look at the Smart Chart. SMART is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool, and it shows the techniques we have available at EAG plotted to show their attributes related to spot size and detection limits. They are color-coded according to the descriptions at the lower left. For example, blue areas provide elemental information primarily, while green techniques show imaging information. The x-axis shows the range of spot size from 1 centimeter at the right down to about 1 angstrom at the far left. And then the y-axis shows concentrations either in atoms per cubic centimeter at the left or in atomic concentrations at the right. This ranges from 100% at the top down to 10 parts per trillion at the bottom. So within this box, you can select your technique based on the detection limit you need and the size of the area of interest. Outside the box are techniques that don't quite belong on this chart. So the techniques on the right, for example, don't necessarily have a spot size associated with them. They are basically bulk composition techniques that, well, may consume your entire sample, and they have the detection range shown from top to bottom. The techniques at the bottom are basically imaging techniques and don't provide compositions per se, but they do have relevance with respect to the spot size on the x-axis. So where does Auger fit in? As you can see, it's one of the stars of the smart window here, pushing the envelope for spot size to the left, where not many other techniques dwell. Its minimum spot size is roughly 10 nanometers or so. The concentration range is about 3 decades, with the best detection limit hovering around 0.1% atomic. If you're curious about some of the other techniques in this chart, you can check out our website at eag.com, and you can listen to a webinar on each of these techniques, and I'll show an upcoming schedule for some of these techniques at the end of this presentation. This figure shows the approximate depth sensitivity of various techniques. As you can see, the idea of surface analysis has a somewhat different meaning depending on the technique being used. Auger probes the top several nanometers, down to 10 nanometers probably, of a sample surface in the same range as XPS and TXRF. You'll note that top SIMS here on the left is even more surface sensitive. And to the right, these techniques sample a bit deeper. Note, however, that really all these techniques are surface techniques, since the maximum depth listed here is about 2 microns. I was reminded of this during the talk I gave at Oak Ridge Laboratories, where I was presenting Auger and RBS results of potassium implanted surfaces, and I mentioned that Auger was surface sensitive and that RBS was not, and I got a strong objection from the audience that RBS can only sense the top micron or so, and it's indeed surface sensitive. It's only looking at a very shallow area anyway. But for Auger, however, this shallow depth of analysis is a strength that leads to better detection limits for very thin films, where it may fall below the detection limit of other techniques that probe a larger volume, like SEM-EDS over here. So as a result of these attributes of Auger analysis, several key applications have emerged that take advantage of these advantages. Because of the very small electron beam diameter, we can observe and detect very small particles and features as small as 25 nanometers. And I would venture to say that we can even detect features smaller than our beam diameter under certain ideal conditions. And by virtue of its very shallow information depth, Auger is key to analyzing very thin layers, even submonolayers. This shallow escape depth also lends itself well to measuring thin film stacks on the order of tens of nanometers thick. We can do this by performing an Auger depth profile that measures composition as a function of depth. So the small analytical depth leads to excellent depth resolution for thin films. Typically, Auger depth profiles do not go much deeper than a micron, although you can if you are not limited by time and money. However, most materials will get rougher as you sputter longer, and this will degrade the depth resolution considerably. For very thick films, it may be more efficient to prepare a cross-section by mechanical polishing or with an FIB, and take advantage of the very small spot size of Auger to analyze the thicker layers in cross-section. In this way, we can also provide compositions versus depth, much like a depth profile. But this time using an Auger line scan across the features of interest. The Auger line scan is a plot of concentration versus distance across an image. Auger is also semi-quantitative, meaning we typically provide compositions based on a set of standard sensitivity factors provided by the instrument manufacturer, but they are not always accurate, though results are typically precise within a few %. More accurate results can be obtained by analyzing standards of similar known compositions under the same instrumental conditions and comparing them to the unknown samples. Okay. So let's take a look at what happens when an electron beam interacts with a solid. Here we have depicted an isolated atom that's about to be bombarded by incident electrons. So when electrons bombard a surface, several things can happen. One of the things that can occur is just backscatter, which is a result of a near collision of the electron with the nucleus, causing a direct change in direction, and but no loss in energy. So we can detect these backscattered electrons as long as they are low enough in energy for our analyzer to detect, which typically is 3 keV or less. And we actually use them to ensure our sample is in the focal plane of our analyzer while we're performing Auger analysis. Much more common are inelastic collisions where there's some loss in energy, sometimes through multiple interactions with the electrons in the solid, and this leads to secondary electron emission, which is used to image the sample, and some Bremsstrahlung decay radiation, which we do not detect. But the event we are most interested in is when the incident electron causes ejection of a secondary electron, leaving the atom as an ion in an excited state, where the missing electron is from a level below the valence band. These excited electrons then relax primarily through 2 ways. An electron can drop down from a higher level to this lower vacant level, but the energy difference is used imparted to an X-ray photon, and this is the basis for EDS. But what every Auger analyst likes to see is relaxation process number 2, where again, electron will drop down to the lower level, but this time the energy difference is used to eject a 3rd electron, which is called the Auger electron. The kinetic energy of this electron is very characteristic of the atom it came from, and it is the difference between these 2 energy levels minus the binding energy of this 3rd electron, or Auger electron. So by energy analyzing these emitted electrons, we can identify the atoms they come from. So I'd like to say a little bit more about the very small depth sensitivity for Auger. So when an electron beam enters the solid, it begins to scatter. The deeper it goes, especially. The primary beam does penetrate quite far into the solid with the beam energies we typically use, like 10 keV, for example. This beam will generate lots of secondary electrons and X-rays within the teardrop-shaped excitation volume you see here. However, electrons cannot travel very far without losing some energy. So in order for us to detect them, they have to travel back towards our detector up here at the surface. These electrons come from depths only up to about 10 nanometers or so, depending on their energy. So this is the tiny yellow bar you see here. This is also advantageous in that the analytical spatial resolution is limited to pretty close to the beam diameter, because at this depth, the primary beam has not had much of a chance to scatter laterally in that depth. So note the depths of some of these other phenomena, and that they're slightly deeper. And this big blue sphere is where we can expect X-rays to come from, since they travel much further in a solid without losing energy. So we get a greater penetration depth, greater information depth for EDS than we do for Auger. Okay, so this is great for surface analysis, but what if we want to go a bit beyond this? So we can introduce the ion beam as a means of removing material and analyzing what's left behind. In Auger, we use argon ion beams that are very inert. To acquire a depth profile, we typically start by analyzing what's present on the surface with its limited escape depth. And then we monitor the peak intensities of the atoms we detected here, plus any we expect underneath. If we don't know what to expect underneath, we can do survey depth profiles, but that consumes a lot of time. During the depth profile, the ion beam is kicked on for a limited amount of time, and then it's stopped, and we analyze the surface with the electron beam, and we repeat this over and over again to obtain the depth profile. The ion beam does not participate in the data acquisition. It's merely used to just get material out of the way so we can see beneath. A typical sputter crater is a few millimeters across, while a typical analysis area is a few microns. So this several orders of magnitude difference ensures that we are analyzing the bottom relatively flat area of the crater and not getting any contribution from the slanting sidewalls, which would degrade our depth resolution. So how do we generate Auger data? Well, we use this cylindrical mirror analyzer, AKA the CMA, with a centered electron gun combined. So here we have a crude schematic that shows a cross-section of the analyzer. The kinetic energy of the electron is measured by scanning a potential between two concentric cylinders. Only the outer cylinder is shown here for clarity, but imagine there is another cylinder just inside. So as electrons are emitted from the solid below, only those electrons with the correct kinetic energy will make it through the analyzer and to strike our detector. And different energies are detected by changing this electric field between the two cylinders. This primary electron beam source is centered within the CMA, so this design ensures that the source and analyzer are collinear, and so you have to only be concerned with the alignment of the area of interest with the electron beam. Since the analyzer is a cylinder, it's a cylindrical shape, it will detect all electrons actually from a multitude of emission angles. So this electron emission intensity is almost independent of the topography of the surface, as long as it's fairly shallow roughness. So this gives a more uniform yield over rough surfaces, enable us to analyze within holes and trenches, etc. So here's one of our Auger instruments I wanted to show you what one looks like. I can point out some of the features of this marvel of engineering. At the top, there's a brown box-looking contraption. This is actually an ion pump that's dedicated solely to maintaining UHV conditions around the source. Our primary beam is a field emitter, and these emitters are very sensitive to surface contamination, so it's imperative that it stays clean for the entire lifetime of the tip. Below that, you can see a couple of cylinders that house the electron gun and the CMA. There's a viewing port here to make sure you haven't dropped the sample after transferring the sample from the small intro chamber here into the main chamber with the use of this long transfer rod, which is coupled to this black handle with rare earth magnets. The large cylinder jutting out towards us contains the stepper motors and drive hardware to move the sample stage in 5 different directions. And then here is our argon ion gun with a thermally controlled leak valve here. So note that this arrangement leaves the 3 important axes for analysis to be in one plane. And this coplanarity geometry helps us to examine samples which have challenging geometries that would prove difficult for other techniques. This whole thing is in an ultra high vacuum chamber, typically in the 10 to the minus 9 to 10 to the minus 10 torr range. These instruments are quite incredible considering you have to have very smooth stage motions and be able to minimize vibration to the at least sub-micron level without using any grease or lubricants for the moving parts that would foul the vacuum. And we also need to get electron signals in and out of the vacuum chamber without introducing leaks. And you need to control fairly high voltages with in a few tenths of a % precision. Here's a look through our viewport. And we can see the sample on our stage. In this system, we are limited to a 1-inch diameter sample holder, but we do have other systems capable of much larger samples. Note that the sample is tilted 30 degrees with respect to the primary beam, which comes from this center cone here. The end of the CMA is this larger cone. This tilt angle enhances our detection of electron emission from the surface, which is strongest in the normal direction. So we tilt this sample towards one of the acceptance angles of the CMA. Off to the left, you can see the end of the ion gun. So what does an Auger spectrum look like? As I mentioned before, we obtain a plot of electron counts as a function of electron kinetic energy. So you can see there's a general slope of increasing signal towards higher energies. This is a feature of the CMA, whereby using higher and higher voltages to bend the higher energy electrons towards our detector, it compresses the energy window that passes through the exit aperture, effectively making more electrons available at an ever wider range of energy. So we get increasing counts with higher energy. So you might see an energy resolution noted about 0.6% of the kinetic energy. So this increases with energy. Towards the lower part of the spectrum, it increases again due to secondary cascade of electrons, which is a lot of this is suppressed by the CMA, but it's still there. You might also discover this background is quite high. The scale is in counts per second, but with a scale factor of 10 to the 6th. So the peak intensities are only a few tenths of this scale. So we are looking at relatively small peaks on a large background. So what is usually reported is the derivative of this spectrum. And mainly for historical purposes, because older analyzer designs had an even higher background, making the peaks barely visible. With the differentiated form, the peaks are enhanced. The background is level due to the gentle slope of the background being more or less constant. And with this differentiated form, we can measure the kinetic energy of the peaks by this negative excursion of the derivative. And we obtain peak intensities by measuring the peak-to-peak amplitudes. So here we can see the peaks for aluminum, oxygen, nitrogen, carbon, some smaller peaks here. This is from a surface of an aluminum nitride sample. So most spectra you'll see will be in this format, although there are some advantages of showing it in this format as well. Okay, so let's see this technique in action. We're gonna start looking at some examples. Here's some typical analyses that we have done over the years. We're gonna start off with a couple of semiconductor applications where we identify contaminant on a pattern wafer, and then look at an aluminum bond pad that exhibits poor wire bonding behavior. I'll also show some examples of analyses of two very important metallurgical alloys used by semiconductor equipment manufacturers and medical device makers, among other people, namely electropolystainless steel and the nickel titanium memory shape alloy. A very interesting analysis on an embrittled steel sample will be shown next, followed by an example of Auger analysis inside challenging geometry of a via. A very popular request for our lab is the identification of particles on full wafers, and I'll show that we have two full wafer Auger instruments capable of quickly identifying submicron particles without breaking the wafer. And finally, if I have the time, I'll show the power of combining Auger and FIB capability to identify a difficult buried defect. So this first example can be summarized in one slide. With our electron beam and an integrated secondary electron detector, we can create SEM images much like an SEM. We use similar beam voltages as dedicated SEMs, but the beam diameter for Auger is at least an order of magnitude larger than the beams used in dedicated SEMs. We need higher current to generate Auger emission, and it's difficult to cram all those electrons in a very tiny beam, so there is some sacrifice to spatial resolution in Auger. If imaging is all you need, it's best to go to a dedicated SEM, but for Auger analysis, we can provide reasonable SEM images. In this image, we can see an amorphous looking thinnish defect spread across a couple of titanium nitride coated aluminum lines over a silicon oxide substrate. We can compare the surface spectrum from this defect with a reference spectrum from a nearby line without the contaminant. So the screen spectrum shows what we'd expect for a tinitride surface that has oxidized somewhat and has a small amount of carbon. And trace aluminum is also observed, possibly arising from beneath the tinitride or from the aluminum sidewall. In contrast, this spectrum, the red one, from the flake shows much stronger aluminum peaks and virtually no titanium is detected. This indicates this defect is aluminum-based. In the lower left figure here shows an Auger map overlay where we measure the peak intensities of aluminum and titanium as a function of location across this same SEM image. So we don't collect full spectra like you see at the right for every point. We only measure quickly the difference between the peak intensities of the peak and compare it to the adjacent background intensity. And so we've done this for aluminum and for titanium, and we color coded the aluminum red and the titanium green in this map overlay. Bond pads are very important to the semiconductor industry as these are formed at the end of the front end manufacturing, and it's important that they perform well after bonding at the packaging stage. So here we see two bond pads with, again, SEM imaging in the Auger tool. One is from a typical bond pad, and the one on the right is from a contaminated device pad that has shown poor wire bonding. And note that the SEM images don't show anything amiss. We can start this off by collecting surface spectra from both pads. Typical one on the left shows strong aluminum, oxygen, and carbon peaks with a somewhat weaker fluorine peak. While it would be preferable to have clean aluminum at this stage, most metals oxidize upon exposure to air, forming a thin layer of oxide, followed by some absorbed organic material on top of that. A small amount of fluorine is somewhat typical for bond pads that have been opened with a fluorine-containing etch, and we will see a little bit of fluorine residue. On the right, we see a much different Auger spectrum from the bad bond pad, and here fluorine is the dominant peak, indicating much higher fluorine intensities than is typical. And here we can also acquire Auger depth profiles to measure the oxide layer thicknesses on these two pads. Here we are again monitoring the peak intensities of aluminum, oxygen, carbon, and fluorine as a function of sputter depth, sputter time in this case. For the good bond pad, we see a relatively thin oxide with some fluorine in it. And note that the carbon layer sits on top of this surface oxide. This oxide layer was measured to be approximately 40 angstroms on this sample. In contrast, the bad sample does not show a well-formed oxide layer. Instead exhibits a long, drawn-out tail towards lower depths. And this oxide thickness was measured to be much thicker, around 1600 angstroms. And this thick of an oxide would be a hindrance to wire bonding. And I'd also like to point out that you'll see two forms of aluminum in both profiles, one in the oxidized form, the other in the metallic form. Auger spectroscopy is mostly an elemental technique, but there are certain situations where we can sense chemical bonding, and aluminum is one of those elements where we see a very large chemical shift in the Auger and in the aluminum peak energies, and the line shapes are also quite different. So we could take advantage of this for several other items as well. We can see this for silicon, some other metal oxides, and we see this for carbides, and some oxyanions of sulfur, phosphorus, and chlorine also, but not much else. Here is an example of a very common analysis request of electropolished stainless steel. The requirements for this alloy in some applications is a very smooth surface, which is not prone to corrosion or show any propensity of flaking or generating particles. So we can examine the surface of these samples, determine if there's any unusual contamination. Here we see the expected steel components, iron, nickel, chromium, carbon, although some of this carbon is undoubtedly adventitious. We see trace amounts of phosphorus and sulfur here, but these intensities are probably well below 1% since we're very sensitive to these particular elements. We can also obtain, again, an Auger depth profile to not only measure the oxide thickness, but also to measure the type of chemistry that's in the oxide. So a well-polished steel should have a chromium-rich oxide at the top, which helps makes the steel passive to corrosive attack. Some of our clients do have strict specifications for the thickness of this oxide and the chrome to iron ratio within this oxide. These samples must show these characteristics in order to be acceptable, and Auger can provide both quite easily. In this case, this oxide was a good one. It's about 30, I think 35 angstroms or so. Another very important alloy is nitinol, a nickel and titanium containing alloy that's proven to be biocompatible. These days, many implantable devices contain nitinol, including stents, like the one shown here. This is a fairly small device, but Auger is quite able to analyze this type of sample easily. I'd also like to point out that we can analyze not only the inner diameter and outer diameter of these stents, say the top and bottom of this particular segment, but we can also characterize the sidewalls and even the inside of this bend shown here. So recall that the analyzer axis and the primary beam axis and the ion beam axis are all coplanar, so all we have to do is to ensure this plane is in the correct orientation to prevent any blockage of the electrons or ion beams from these side struts. And in this case, that would be in and out of the plane of this figure. And we could analyze this inner part here fairly well, although the count rates will be diminished somewhat by the presence of these sidewalls blocking some of the electron emission. We can start off this analysis with the surface survey from an area that we can draw on our SEM image. In this case, it's about a 10 micron square area. This spectrum revealed the presence of titanium, nickel, oxygen, and carbon. All are pretty much expected, with small amounts of sulfur and phosphorus. Sorry, potassium. We expect from a nicely passivated nitinol sample mostly titanium and oxygen, but we do not want to see much nickel at the surface, as that leads to nickel leaching. However, recall that Auger emission can come from a few monolayers beneath the surface, so this small nickel signal may arise from beneath the surface. And we can also obtain a typical depth profile. Well, this is an example of a typical depth profile of a nitinol stent. This is a well-formed titanium-rich oxide on this sample, about 56 angstroms thick. So this is what we'd expect. We want it to be titanium-rich here, and then we'll see the nickel enrichment just below this, and then we'll achieve bulk composition deeper into the solid, which we're not quite there yet. So in situ steel fracture of a brittle steel sample. Here's a sample from a rotor blade that was inserted into an Auger system, which had a fracture attachment that allows for fracturing of samples in the vacuum at 10 to the minus 10 torr. This preserves the original fracture facets without oxidation and carbon absorption that would occur if this was done in air. This attachment also has the capability of cooling the sample to liquid nitrogen temperatures, which enhances brittle fracture modes. And that also occurred in this particular case. The SEM images after the fracture show very, very sharp granular edges, typical of intergranular separation. We can zoom in and focus on an individual grain and note how highly textured the grain faces are. We can zoom in even further and take note of any features that we may want to analyze later, like precipitates or grain boundaries, that sort of thing. Now here we show a high magnification SEM image and a corresponding Auger map overlay. So in this case, we've chosen blue for iron, red for antimony, and green for chromium. Just a reminder, Auger maps are just figures that display relative elemental peak intensities at points that correspond to the SEM image shown here at the left. So here we see that this grain phase is mostly bluish, so it's mostly iron as expected, but there are regions where chromium has concentrated. They're very much more green. And it is troubling to see that there is so much antimony present, which is not a component of steel typically, or not that much. And antimony is a known contributor of embrittlement in stainless steel alloys, and so that explains why this particular piece was prone to fracturing. Once we have the SEM image and the Auger map overlays, we can select specific points and obtain full spectra from these points to see if we have accounted for everything. So we take a look at a spot here in the red area, and we do indeed show strong antimony peaks along with strong iron peaks and some nickel. We look at the blue area, and that's almost entirely iron and some nickel. This green area we expect to be chromium rich, and indeed it is. We see higher chromium and we see higher carbon, and it turns out these are chromium carbide areas. And then something happens down here in this green area where we do see higher chromium than is shown in these other areas, but we also see a very strong peak for sulfur, which was not expected. This slide shows more results from just this one sulfur-containing particle. We can zoom in even further, and we show here an Auger map overlay of iron, chromium, and sulfur this time. So the red sulfur map plus the green chromium map together give this yellow color on this precipitate, indicating that this particle is chromium sulfide. So a precipitate of chromium sulfide is shown here. Note that this size of this particle is only 100 nanometers or so. Here's a SEM image of an array of vias that was supposed to be filled with tungsten, but you can see that the coverage is very uneven. The question was whether or not some contamination was preventing the nucleation of the tungsten on the aluminum surface, which is at the bottom of each via. And this is a great application for Auger, where we can take advantage of the small spot size to look inside these 1 micron diameter vias, roughly 1 micron. We take advantage of the CMA geometry and its multiple takeoff angles for Auger electron detection for this geometry. And take advantage also of the surface sensitivity of the technique to detect if there's any thin layers of contamination. In this via, I show just the Auger map overlay for silicon in blue, tungsten in red, and aluminum in green. So you can see that the bright particles are tungsten, where it did successfully nucleate. In fact, you can see that the red areas are a bit larger than the bright white areas, and you can see maybe faintly there is some tungsten nucleation here and these other sites, and some faint sites over here that correspond to these red areas. And in between here, we just see aluminum. And so these results, plus some other results not shown, spectra within this area, indicated that there was no surface contamination on the aluminum. We see clearly aluminum present in all these other areas. So this indicated that the problem was with the CVD chemistry or the deposition conditions, which led to the bad nucleation results here. So before we begin with the full wafer particle analysis, I'd like to show our best full wafer Auger system that produced these results. This instrument is in our Minnesota laboratory, and it has 300 millimeter wafer capability. We can take a full wafer cassette from our clients and introduce them into this Auger system without exposing them to normal air, providing many more particles if we do that. The system has the same features that the earlier instrument I showed you has, except the vacuum chamber, of course, is much larger to accommodate the much larger samples. And we're hiding all the cool stuff within these steel enclosures to give it this nice, clean appearance. So there are several nice defect review tools out there that can inspect full wafers, patterned or unpatterned, and identify defects and their locations on the wafer. Many of them provide a size measurement as well for these defects. So they can typically output a wafer map which shows the location where these defects are and provide a table of these locations in coordinates. Our full wafer Auger instruments here at EAG can read these files directly from most of these instruments. And once we have calibrated our stage, and sometimes we have to translate the axes, we can have our full wafer stage navigate directly to any of these particles. And then once we're there, we can provide a SEM image of the defect, which we can pass on to the client so they can compare this image to their own images, giving us all confidence that we're examining the same particle. But more importantly, we can provide an Auger spectrum from the surface of this particle, giving our clients the elemental makeup of this particle. Here's example, or some examples of what an Auger analysis report might look like, showing just the particle SEM images and the Auger spectra from the surface of these particles and after a light etch to remove surface contamination. And here we've identified two copper particles, these two. We've got an aluminum particle here, and we've got an oxidized aluminum particle here. This one being only 16 nanometers, and all of these particles are less than 50 nanometers in diameter. So this is quite a powerful tool for measuring several particles on a wafer. And here our last example shows a somewhat larger particle. It's a bit of a puzzle at first. So the initial surface analysis showed the same elements on this particle, this defect, as there was on the outside area. So there's tungsten silicide, and it's got surface oxidation with a little bit of carbon, which we'd expect. So at least on the surface, there's nothing that would identify what this particle is. Well, why is it there? In this case, the analysts use an in situ FIB tool to cross-section this particle and examine it further with Auger. The full wafer systems at EAG have this FIB capability where we can make cuts in the same vacuum chamber as the Auger instrument, preventing any oxidation and carbon absorption from exposure to air. We also have the support of many state-of-the-art standalone FIB tools or dual beam instruments that can provide beautiful cross sections, which we can examine in the Auger, albeit with the caveat that the cross-sectional face will oxidize during the transfer between instruments. So here we can see three spectra obtained from this cross section. The first one in red coming from a dark area that resides underneath the particle, but above the substrate. So this red spectrum revealed the strong peak from carbon, much higher than you see in these other areas from below 0.2, which was mostly silicon, and above, which is tungsten silicide, the cyan colored spectrum. And like I always like to do, I like to show map overlays, nice colors. So based on the surveys and the Auger map, the Auger SEM images, we can accumulate Auger maps, overlay them like this, and we do find that the high carbon intensities do correlate very nicely with the shape of the defect. So this result shows the power of using multiple techniques to investigate a problem, something that we can do quite easily here at EAG, since several of our labs have a lot of these techniques in the same building. So to summarize, what I've tried to show today, Auger is very surface sensitive, enabling us to detect submonolayers of material on the surface. The surface sensitivity also lends itself to good depth resolution, So we can provide depth profiles to determine compositions of thin film stacks down to tens of nanometers thick. And another strength of this technique is its very small spot size, lending us the opportunity to analyze submicron particles and features. Now, some of the limitations of the technique are we do need standards with similar compositions as the samples of interest for best quantification. The precision for Auger analysis is very good and can be used to compare samples, but for best accuracy, standards are needed. Insulators are difficult to analyze with Auger because we are using an electron beam of very high current density, and if that current does not flow to ground, eventually it will lead to charging of the sample that will distort SEM images and make energy analysis of the emitted electrons difficult, enough impossible. But having said that, I am of the opinion that it is possible to obtain an Auger spectrum from everything, but you have to give up some of the advantages of the technique to do so, like giving up spot size or using lower energies, which will lower your detection limits for Auger peaks of higher energies. It may also require a thin metal coating to make it slightly conductive, which will compromise your surface sensitivity. And finally, of course, the samples must be vacuum compatible, so no greases, no liquids, obviously, or any other volatile materials. Other techniques we have here at at EAG can be used to extract more information from your samples and make up for the limitations of Auger analysis. XPS, very similar surface analysis technique, generates binding energies of photoelectrons from X-ray sources, so it can handle insulators quite easily, and has a fairly decent spot size of some tens of microns, 100 microns or so. Auger cannot provide much information, chemical information for organic compounds, but Raman can be used on areas as small as a micron to identify small organic or organometallic particles. SEM EDS, I mentioned before, has excellent imaging resolution, offers very good elemental analysis for areas and down to depths of about a micron or so. For the ultimate in spatial resolution, you can go to STEM with EDS and EELS, energy electron loss spectroscopy, to identify elements. And then finally, we do lots of analysis with TOF SIMS, which has an excellent detection limit of parts per billion and a fairly decent spot size over here of a few microns. We've also combined Auger analysis with almost every other technique in this chart, but I really don't have time to discuss all the merits of these possible combinations right now. So I want to mention here that EAG is ISO 17025 and 9001 certified. We are audited on a regular basis by such organizations as the A2LA. We have a quality system in place for our Auger systems where we check the performance of our instruments on a weekly basis and conduct a more thorough investigation testing annually. We are a global leader, we feel, for materials testing services with a broad range of instruments and expertise. Leave us poised to take on even the most challenging materials and engineering related issues. I just recently discovered that EAG owns more than 2,500 instruments worldwide. So you can see that EAG has made and continues to make a substantial investment in instrumentation to serve our customers. And we also take client confidentiality very seriously in our company with protocols in place for export control as well. In light of this pandemic affecting the world right now, I also would like to mention that EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID-19 regulations from state and local governments, as well as the Centers for Disease Control. Currently, all of our locations throughout the world remain open, but we may have limitations on customer visits. So as this is a fluid situation where we are operating a laboratory at reduced capacity, we can also transfer your samples to another EAG location. So we encourage you to discuss your options with your sales representative.